we want to get used to sort of reading information off of our PV diagrams. So we've got P and V, and if we go from this point to this point, this would be isobaric, like that. The work from done is the area under the curve, right? Because the work is this integral. In this case, it's just P delta V. Okay, this is V initial and this is V final. And this, using this, we can find the work that's done. We can use the change in internal energy to then put that together with the first law of thermodynamics. This is the first law. And find the heat. But I want to point out that if we have a situation where we have PV and we start at a high volume and go this direction, right? This is our initial and this is our final. Then this here, this work is less than 0. Okay, it's negative work. It's work done on the gas as you compress the gas. And so, I mean, work is still pressure times delta V in this case. It's just your final is smaller than your initial. So when you do work is equal to pressure, V final minus V initial, this term is bigger, this term is smaller. So you can think of it as a big number and a little tiny small number. And so overall you get a negative value. Now we can take a situation like this and we can make what's called a cyclic process, which means we go back to our starting point. So cyclic, not cylinder, cyclic process just means like we start here and let's say we do an isobaric expansion, the volume gets bigger, then we keep the volume the same and drop the pressure. Okay, so here, so this is going to be step 1, and then we're going to have step 2 like this, okay, and so the work for step 2 is going to be 0. This is the work for step 1, and that's going to be greater than 0, and then I'll just keep using new colors. This is the work. This is step 3, let's say step 3. And so the work for step 3, we calculate the same way, but it's less than 0. And then finally, when we finish this up, we'll go back to here in step 4. And the work for step 4 is equal to 0. Now the work for step 1 is positive. The work for step 3 is negative, but they don't cancel out. Notice that work 3 is just this area under the curve, and where this sort of orange and blue meet, they cancel out, but the net work that's done is this inside place, right? So the net work, so the total work, we add up the positive and the negative, the net work in this situation is going to be positive, and it's the area of that enclosed square, the enclosed area, if you like, because that's just what we get when we take the integral. And it doesn't have to be a square, right? It can be any shape. But when we circle back around, the net work is greater than 0, but the change in internal energy for the whole cycle, because we end up at the same pressure and volume, same number of particles. If we're at the same pressure, volume, and same number of particles, PV equals nRT or PV equals nKBT, either way, we're at the same temperature, so we end up at the same place and our internal energy change is 0. Okay, so by energy conservation, that says that the heat, that the work, which means that just using the first law, that the heat must go into the work, right? So if we look at this, this is a situation where on step 2, for example, the work is equal to 0, the temperature is decreasing. So for step 2, the temperature is going down, and so the heat is, the internal energy is negative, Q is less than 0, and delta E internal is less than 0. This is all step 2 information. For step 4, work is equal to 0. Delta E internal of step 4 is greater than 0, which means the heat is greater than 0. So this is all step 4. And we can do the same kind of analysis and find out, in fact, that we have heat that goes in here, and it goes in here. Q is going in these steps, and it's going out in steps 2 and 3. Okay, so that's sort of our setup. And in fact, the heat equations, if you look back at what we did, we can find that the heat equations look like this. That for constant volume, right, steps 2 or 4, the internal energy must equal the heat. So constant volume, we have the heat. Constant volume looks like 3/2 in kb delta T. So the heat in tells you how much the, kb delta T, or we can write this as 3/2 in R delta T. And so what we do is we recognize that the heat capacity, the molar heat capacity, this heat capacity, CV, is 3/2 R. That's the heat capacity for a constant volume case, okay? So we're trying to get something similar to what we did before with liquids and solids, where we said heat was equal to mc delta T, right? Well, we've got similar, but we have to be really careful. It depends on whether the volume's constant or the pressure's constant. So if we go to a pressure constant situation, so a constant pressure, then Q at a constant pressure, Q is internal energy plus the work, and the work is given by this, and we found that this was equal to 5/2 in kb delta T, or 5/2 in R delta T. So the specific heat at constant pressure is 5/2 R, okay? And so this gives us a sort of our equivalent specific heat or heat capacity type equation. It tells us how much heat added gives us a change of temperature. Obviously, if we add heat for an isothermal, that's a constant temperature process, then we haven't changed the temperature. But these are ways that we change the temperature at constant volume and constant pressure processes. Now, this all really has, right, our usual asterisk here, all of these. This asterisk says, hey, this is for monatomic ideal gas. If you remember our discussion of equipartition, we have to do something different here. Okay, so this is all for monatomic, but you may or may not remember that when we were talking about diatomic, we said if we have something that's diatomic, so we have something like this, and we think of it as rigid, so vibrational energies don't come into play, then our change in E internal gets 2 more degrees of freedom. So instead of 3/2, we have 5/2 in our delta T, or 5/2 capital N kb, Boltzmann's constant, times delta T. So it turns out that this, of course, because we use this to then get our specific heats, our heat capacities. So for a diatomic, we have CV is equal to 5/2 R, and we have, similarly, we have CP now is 7/2 are if we have a diatomic molecule where vibrational energy doesn't matter. So no vibrations. And that's typical in sort of room temperature and above, not way above, but in sort of the temperatures we're mostly working with. And if we have a polyatomic, more than 2, then we change this, and this becomes the change in internal energy is equal to, we get 1 more degree of freedom associated with 1 more degree for rotation. So this becomes 6/2 or 3 in our delta T. And so that means our CV becomes 3R and our CP becomes 4R. Finally, it's useful for us to identify a constant that we're going to use a little bit later, and this is gamma. That is the ratio of CP to CV. So for the monatomic case, right, monatomic, this is pretty straightforward, that would be gamma is equal to 5/2 R over 3/2 R. The R's and the 2's cancel, and this just becomes 5/3. So this is a way to designate a way to describe whether we've got monatomic, diatomic, when we have no vibration. When we have vibrations, we add another 2 1/2 here. So instead of this being 5/2, this suddenly becomes 7/2. But we don't generally get to those temperatures. So then, just for completeness, diatomic is just going to be gonna have a gamma of 7/5, and then any material that's made up of more than 2 atoms, so 3+ atoms, we're going to have a gamma generally then of 4/3, okay, 1.3, thereabouts. Okay, so that's those are the values, and we'll see this shortly when we start to talk about something called an adiabatic process.